Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can slow down, stretch out, and wander gently through some of the deepest questions ever asked. Tonight, our journey begins with something very simple: an apple. Not an abstract idea, not a distant galaxy, not a mysterious equation. Just an apple resting quietly in the palm of your hand. Imagine it for a moment. The smooth skin catching a bit of soft light. Perhaps it is red or green or somewhere in between. You can almost feel the cool weight of it, the faint scent of sweetness rising from the surface. If you tap it lightly against the table, it makes a small, satisfying sound. If you take a bite, there is a crisp snap, followed by the gentle taste of fruit and sunlight and soil. In moments like this, reality feels perfectly obvious. The apple is real. The table beneath it is real. The room around you is real. These things seem solid, reliable, unquestionable. They occupy space. They resist your touch. They exist whether you are looking at them or not. For most of human history, this simple experience was enough. Reality was what you could see, touch, hear, taste, and smell. If something could be sensed, it existed. If it could not be sensed, it probably did not. And in everyday life, that idea works remarkably well. When you place the apple on the table, it does not drift through the surface like a ghost. When you drop it, gravity pulls it downward with dependable patience. When you bite into it, the texture and flavour arrive exactly where you expect them to. Reality, it seems, behaves politely. But if you pause for a moment and look a little more carefully, something curious begins to appear. The apple that feels so simple and solid may not be as straightforward as it first seems. Let us imagine that we decide to investigate it more closely. Suppose you take a knife and cut the apple in half. Nothing surprising happens. You simply see the pale interior, the seeds arranged in a quiet star shape at the centre. Now imagine cutting one half again, and then again. Smaller pieces, thinner slices, fragments so tiny they begin to lose their familiar shape. At first, you're simply dividing fruit. But if you could keep going, smaller and smaller, far beyond what the eye can see, you would begin to discover that the apple is not really made of continuous material at all. Instead, it is made of cells, tiny living compartments, each surrounded by delicate membranes, each performing quiet chemical work. A single apple contains millions of them, each one a small world of molecules and reactions. If you could look deeper still, those cells would dissolve into molecules. Complex arrangements of atoms linked together like miniature structures, each one dancing with invisible energy. And then, going further still, those molecules would reveal the atoms themselves. Atoms were once imagined as the smallest pieces of matter, tiny solid beads forming, the foundation of everything. For centuries, many scientists believed that once you reach the atom, you had finally arrived at the ultimate building block of reality. But the story does not stop there. Inside every atom is a small central core surrounded by a vast region where lighter particles move in strange and subtle patterns. And if you could shrink yourself enough to explore that tiny domain, you would discover something astonishing. Most of the atom is empty. Not just a little empty, but overwhelmingly empty. If the central core of the atom were the size of a marble sitting in the middle of a great cathedral, the nearest electrons would be drifting somewhere near the outer walls. Almost everything in between would be open space. And yet, when you press your finger against the apple, it feels completely solid. Your hand does not pass through it. The apple does not collapse into a cloud of invisible particles. It behaves like a solid object, dependable and firm. So already we have encountered a small mystery. At the scale of everyday life, the apple is solid and simple. At the scale of atoms, it is mostly empty space arranged in delicate patterns. Both descriptions are true, they simply belong to different layers of reality. And this is where our journey truly begins. Because the deeper scientists have looked into the nature of matter, the more they have discovered that what appears solid and ordinary from a distance often becomes strange and unexpected when examined closely. The apple on the table is not merely fruit, it is a vast collection of tiny structures, patterns and movements that your senses quietly simplify into something easy to understand. Your brain does not show you atoms, molecules, or empty space. Instead, it offers a smooth red surface, a pleasant smell, a crisp taste. It presents you with an apple, and that may be exactly what reality is like on many levels. The world we experience might not be the deepest layer of existence, but rather a kind of useful translation, a gentle summary created by our senses and our minds. Just as a map simplifies a landscape, your perception may simplify the universe. The mountains, rivers, and valleys of deeper reality may exist beneath the surface, even while the map remains accurate enough for everyday travel. And so tonight, we will follow this quiet question wherever it leads. If the apple in your hand is not exactly what it seems, then what is it really made of? What lies beneath the layers of fruit, cells, molecules, and atoms? And more importantly, when we finally reach the deepest level we can imagine, will we still find something we recognize as real? Or will reality itself begin to dissolve into something far more mysterious? When we left our apple resting quietly on the table, it seemed simple, solid, complete, a small piece of the ordinary world. But curiosity has a gentle way of asking one more question. What happens if we look a little closer? Imagine again that apple in your hand. You take a knife and slice it in half. The blade passes cleanly through the fruit, revealing the pale interior and the small seeds nestled inside. Nothing mysterious yet, just fruit being fruit. But suppose we keep going. You slice one half again, then another. Smaller wedges, thinner slices, tiny fragments scattered across the cutting board. At some point, the pieces become so small that you can no longer hold them easily between your fingers, and if we had a microscope waiting nearby, we could take one of those tiny fragments and place it beneath the lens. Suddenly the apple would stop looking like fruit at all. Instead of smooth flesh, you would see an intricate landscape made of countless tiny compartments. These are the apple's cells, each one surrounded by a delicate boundary and filled with a busy interior where chemistry quietly unfolds. A single apple contains millions of these microscopic rooms, each carrying out its own work. Some are storing sugars produced by sunlight. Others are maintaining the structure that gives the fruit its firmness. Each cell is alive in its own quiet way, part of a community working together to create the apple we recognize. Already the apple feels less like a simple object and more like a small ecosystem. But curiosity rarely stops at the first hidden layer. If we could somehow look deeper still, those cells would no longer appear as the smallest structures. The walls of the cells would dissolve into chains of molecules, delicate arrangements of atoms linked together like tiny pieces of architecture. Molecules are the shapes that chemistry builds. Some of them carry sweetness, others give the apple its crisp texture. Others still are responsible for the faint scent that drifts upward when the fruit is freshly cut. Even though these molecules are far too small for our eyes to see, they determine much of what we experience when we bite into the apple. The taste, the smell, the softness of the flesh all emerge from their invisible arrangements. Yet even molecules are not the final step in the journey inward. Each molecule is made from atoms. For centuries, atoms were imagined as the smallest possible pieces of matter. The word itself comes from an ancient idea meaning something like uncuttable, the last fragment that could not be divided any further. It was once tempting to imagine atoms as tiny solid beads, like miniature grains of sand making up the entire universe, and for a while that picture seemed reasonable. But when scientists finally learned how to probe the atom itself, something unexpected appeared. Inside the atom is a small central core surrounded by lighter components, moving in patterns that are both subtle and strange. And the space between them is enormous compared with their size. To picture this, imagine a great cathedral hall. In the very centre of the hall sits a single marble. That marble represents the dense centre of the atom. The rest of the cathedral, stretching outward to the walls and ceiling, represents the space where lighter components move. Almost everything inside that cathedral is empty space, and yet, when billions upon billions of atoms gather together, the result is something that feels perfectly solid. Your hand presses against the apple, and it does not collapse like mist. The table beneath it supports its weight. The knife meets resistance when it cuts through the fruit. Somehow, a structure made mostly of empty space behaves like something firm and reliable. This is one of the first quiet surprises waiting beneath the surface of everyday reality. The apple feels solid because countless atoms are arranged in stable patterns, and the forces between them prevent them from passing easily through one another. Even though each atom contains vast regions of empty space, the collective structure they form behaves like a continuous object. From a distance, the details blur together, just as a field of grass looks like a smooth green carpet from far away. A dense collection of atoms appears to our senses as a solid surface. The apple becomes simple again, but the closer we look, the more that simplicity dissolves into layers. Cells made of molecules, molecules built from atoms, atoms themselves composed of smaller pieces arranged in ways that challenge our intuition. Reality begins to resemble a set of nested worlds, each one hidden inside the next, and this idea will guide us for the rest of our journey. Because every time scientists believed they had reached the deepest layer of matter, a new level of structure quietly appeared beneath it. The apple that seemed so ordinary now begins to feel like a doorway. Not a doorway to something supernatural or mystical, but a doorway to the astonishing complexity hidden within the physical universe itself. From the outside, it is fruit resting on a table. From the inside, it is a vast arrangement of tiny structures, patterns, and interactions that our senses gently simplify into something familiar. The world we experience may be only the surface of a deeper architecture, and the deeper we explore, the more surprising that architecture becomes. If we continue this quiet journey inward, something remarkable begins to appear. The apple resting on the table, which once seemed so simple, has already revealed itself to be made of cells, molecules, and atoms. Yet for a long time in human history, atoms themselves were only an idea. Ancient thinkers had imagined them as the smallest possible pieces of matter, tiny building blocks from which everything else was assembled. But for centuries, no one had actually seen evidence that atoms truly existed. They were more like a clever hypothesis than a confirmed part of reality. The first real clues appeared in an unexpected place, a glass of water sitting quietly beneath a microscope. In the 19th century, scientists observed tiny grains of pollen floating in water. At first glance, the grains looked still, suspended peacefully in the liquid. But when magnified under a microscope, something strange happened. The pollen particles danced. They moved in tiny, jittery paths, constantly shifting in random directions as though an invisible breeze were nudging them from all sides. This motion was not smooth like the drift of a leaf across a pond. Instead, it looked restless and unpredictable, a delicate trembling that never seemed to stop. For many years, no one knew why this happened. Then scientists realized something subtle and profound. The pollen grains were not moving on their own. They were being bumped by countless invisible particles in the water itself. Those invisible particles were molecules, and the molecules in turn were made of atoms. The tiny trembling motion of the pollen grains became one of the first clear pieces of evidence that atoms were not just philosophical speculation. They were real physical entities constantly moving and colliding in the hidden world beneath our senses. Reality had just become deeper. Once scientists accepted that atoms truly existed, they naturally began asking the next question. What exactly is inside an atom? At first, many people imagined atoms as tiny solid spheres, almost like miniature billiard balls. It was an intuitive picture. If matter was made of atoms, and atoms were the smallest pieces, then perhaps they were simply very small chunks of solid substance. But early experiments soon revealed that this picture was incomplete. One of the most famous investigations involved a simple yet elegant setup. Scientists directed a thin stream of energetic particles toward an extremely delicate sheet of metal. The sheet was so thin that it contained only a few layers of atoms. According to the earlier idea of atoms as solid beads, most of the incoming particles should have bounced directly backward, like pebbles thrown against a wall. Instead, something very different happened. Almost all of the particles passed straight through the metal sheet as if it were nearly empty. Only a tiny fraction were deflected sharply. This surprising result forced scientists to reconsider the structure of the atom. The experiment suggested that nearly all the mass of the atom must be concentrated in a very small central region, while the rest of the atom was largely open space. To imagine this, it helps to return to the image of a vast building. Picture yourself standing inside a great cathedral hall. The ceiling rises high above you, and the stone walls stretch outward in every direction. In the exact centre of this enormous space sits a single marble. That marble represents the dense centre of the atom. Everything else in the cathedral represents the region where lighter components move around it. If the atom were scaled up to the size of that cathedral, the central core would be smaller than a marble, while the rest of the interior would be mostly empty. And yet, when trillions upon trillions of these atoms gather together, they form objects that feel solid to the touch. The apple resists your bite, the table supports your weight, the floor beneath your feet feels firm and dependable. This creates a quiet paradox. Matter is made mostly of empty space, and yet the world feels solid. The explanation lies in the interactions between atoms. When the outer parts of atoms approach one another, the forces between them become extremely strong. These forces prevent atoms from passing through one another easily, creating the sensation of solidity. From a distance, the enormous emptiness inside atoms disappears from view. Our senses simply average everything together, just as sunlight shining through a window can reveal countless dust particles floating in the air. But from across the room the air still appears perfectly clear. The microscopic emptiness of atoms vanishes when billions of them are packed together. The result is the everyday world we experience. A chair feels solid, a wall feels immovable, an apple feels crisp and real in the hand, yet beneath that familiar surface lies a structure that is far more spacious and delicate than intuition would ever suggest. In fact, if the empty space inside atoms were somehow removed from all the matter in your body, the entire human population could theoretically fit into a space far smaller than a city, and still the total mass would remain the same. It is a strange thought to hold gently in the mind before sleep, that everything we see around us, every mountain, ocean, forest, and star, is built from structures that are mostly empty space. Reality, it seems, is not quite as solid as it appears, but this discovery was only the beginning. Once scientists realized that atoms were mostly empty, they began to explore the tiny central region where the mass of the atom resides. And inside that region, they found even smaller components, interacting in ways that would eventually lead to the strange and beautiful ideas of modern physics. The apple on the table had already revealed several hidden layers of structure. Yet the deeper we travel, the more reality begins to change its character. Solid objects dissolve into patterns of particles. Particles themselves begin to behave like waves. And the quiet certainty of the everyday world gradually gives way to a universe filled with probability, connection, and subtle motion. But before we step into that even stranger territory, it helps to pause and reflect on the discovery we've just made. The world that appears firm and continuous to our senses is built from structures that are mostly open space, and yet those structures hold together with remarkable stability, forming the dependable reality in which we live our lives. The apple remains on the table. Your hand can still lift it. Reality has not vanished. It has simply become deeper. By now, the apple resting on the table has already changed in our minds. Not long ago, it seemed like a simple object, solid and straightforward. But when we looked more closely, we discovered layers of hidden structure beneath the surface. Cells gave way to molecules, molecules to atoms, and atoms revealed enormous regions of empty space surrounding a tiny center. Reality, it seemed, was already more mysterious than our senses first suggested. But the surprises do not end with the structure of matter itself, because the way we experience the world, the colours we see, the sounds we hear, even the sense of solidity when we touch an object, is not a direct copy of reality. Instead, it is something our brains quietly construct. Consider colour for a moment. When you look at the apple, you might see a deep red surface reflecting the light of the room. That redness feels as though it belongs to the apple itself, as if the fruit carries that colour within it. Yet if we look more carefully at what is happening, the story becomes subtler. Light from the environment falls onto the surface of the apple. Some parts of that light are absorbed, while others are reflected outward. The reflected light then enters your eyes, where delicate cells respond to different portions of that incoming light. These signals travel along nerves to the brain, where they are interpreted and assembled into the experience we call red. The colour itself does not exist inside the apple in the simple way we often imagine. Instead, it is the result of a conversation between the light, the eye, and the brain. The apple participates in the process certainly, but the sensation of redness comes alive only within the mind that perceives it. Sound offers a similar example. When a bell rings, the metal vibrates and pushes against the surrounding air. Those gentle waves travel outward until they reach your ears. Tiny structures inside the ear respond to those vibrations and convert them into electrical signals that the brain can interpret. Inside the brain, those signals become the sound of the bell. From our everyday perspective, it feels as though the sound lives inside the bell itself. But in truth, what exists outside is only motion in the air. The sound we hear emerges when the brain transforms that motion into experience. Taste and smell follow the same quiet pattern. The sweetness of the apple comes from molecules interacting with specialized receptors in the mouth. The faint fragrance of the fruit comes from other molecules drifting through the air and reaching receptors inside the nose. In each case, the brain translates patterns of chemical interaction into sensations: sweetness, aroma, texture, colour, sound. These familiar features of the world are not simply waiting out there in space. They arise when physical signals meet the remarkable interpretive abilities of the nervous system. In a sense, the brain acts like an artist quietly painting the world we experience. It takes signals from the environment and transforms them into a vivid picture that feels complete and coherent. This translation works so smoothly that we rarely notice it happening. Yet the idea becomes even more fascinating when we remember that humans are not the only creatures perceiving the world. Different animals experience reality in different ways. Bees, for example, can see patterns on flowers that are invisible to human eyes. These patterns reflect parts of light that we cannot detect, guiding the insects toward nectar hidden at the center of the blossom. To a bee, a flower may look like a glowing landing strip. To us, the same flower appears as a simple patch of color. Dogs experience the world through scent with a sensitivity far beyond our own. What seems to us like an ordinary walk through a park may feel to a dog like reading an intricate story written in invisible trails of smell. Some snakes can detect warmth from living creatures even in darkness, sensing subtle differences in temperature that guide them toward prey. And deep in the oceans, certain animals see flashes of light produced by living organisms, turning the darkness of the water into a landscape of glowing signals. Each species perceives a different version of reality. The physical world remains the same, but the experience of it changes depending on the senses available to the observer. Humans see a particular slice of reality. Our eyes respond to only a narrow band of the light that fills the universe. Our ears detect only a limited range of vibrations in the air. Our noses and tongues recognize only certain molecules among the countless drifting through the environment. The rest passes quietly unnoticed. This does not mean that our experience of the world is false. Far from it. Our senses evolved to help us survive, to guide our movements and decisions in ways that are practical and reliable. But it does suggest that what we experience is not the complete picture. Instead, it may be something like a carefully designed interface. Imagine a computer screen, displaying icons that represent complex processes inside the machine. The icons are not the processes themselves, they are simplified symbols that allow us to interact with the system easily. In a similar way, the colours, sounds, textures, and tastes we experience may be simplified signals. Useful translations that help us navigate reality without revealing every detail beneath the surface. The apple in your hand feels red, crisp, and sweet. Those sensations are real experiences, meaningful and vivid, yet beneath them lies a deeper world of molecules, atoms, and interactions that our senses quietly convert into something understandable. Reality, it seems, may be richer and more intricate than the picture our minds present to us. The brain gives us a map of the world, but like any map, it leaves out enormous detail. And once we begin to notice that translation taking place, a new question begins to emerge. If our senses present only a simplified version of reality, then what does the deeper world truly look like? What exists beyond the colours and sounds that our minds assemble? The apple still rests calmly on the table, but behind its familiar appearance lies a universe far more subtle than our senses alone can reveal. Long before microscopes, laboratories, or scientific instruments existed, human beings were already asking a quiet and powerful question. What is truly real? For most of our daily lives, the answer feels obvious. The world we see around us appears stable and reliable. We wake each morning to the same sky, the same landscape, the same familiar objects waiting where we left them. Yet thoughtful observers in the ancient world began to wonder whether the reality we experience might only be part of a larger picture. One of the most famous reflections on this question comes from the Greek philosopher Plato, who lived more than 2,000 years ago. To explain his idea, Plato invited his listeners to imagine a strange scene. Picture a group of people who have lived their entire lives inside a deep cave. They sit facing a stone wall, unable to turn their heads. Behind them burns a fire, and between the fire and the prisoners, other figures pass back and forth carrying objects. The firelight casts shadows onto the cave wall in front of the prisoners. Because the prisoners have never seen anything else, those moving shadows become their entire world. The shapes on the wall appear to be real objects. The flickering forms seem to represent animals, people, and tools. To the prisoners, the shadows are reality itself. Now imagine that one prisoner is suddenly freed. At first, the prisoner turns toward the fire and sees the objects that were casting the shadows. The shapes on the wall were not the true objects at all, but merely projections created by light. If the prisoner continues the journey and climbs out of the cave entirely, something even more astonishing happens. For the first time, the prisoner sees the outside world illuminated by the sun. The brightness is overwhelming at first, but gradually the eyes adjust, and the former prisoner begins to understand that the shadows inside the cave were only faint reflections of a richer, brighter reality outside. When Plato told this story, he was not simply describing a cave. He was describing the human condition. According to Plato, the world we experience through our senses may be similar to those shadows on the cave wall. The things we see and touch might be only imperfect reflections of deeper and more fundamental forms of reality. For Plato, the true essence of things existed in a realm of perfect forms. The objects we encounter in everyday life were temporary and incomplete versions of these deeper patterns. A beautiful flower, for example, might fade and disappear, but the idea of beauty itself, the pure form of beauty, would remain unchanged. Even though modern science approaches reality very differently from Plato's philosophy, his story captures an important insight that continues to echo through centuries of thought. The world we experience directly may not be the deepest level of reality. Just as the prisoners mistook shadows for objects, we may sometimes mistake appearances for underlying structure. In the sessions before this one, we have already begun to see hints of this idea. The apple that appears smooth and solid reveals hidden layers when examined closely. Cells lead to molecules, molecules lead to atoms. Atoms contain vast spaces and delicate components moving in patterns we cannot see. Each deeper layer changes our understanding of what the apple truly is. From the outside, it remains fruit resting on a table. From the inside, it becomes an intricate network of structures and interactions invisible to the senses. Plato did not know about atoms, molecules, or the hidden architecture of matter. Yet his story suggests something similar. The possibility that the world we see is only a surface layer of a deeper reality. But Plato's vision also contained a challenge. If the world of appearances might mislead us, how can we discover the deeper truth? For Plato, the answer lay in careful reasoning and philosophical reflection. By thinking clearly and examining ideas closely, the mind could gradually move beyond the shadows of everyday perception. Centuries later, another approach would emerge. Instead of relying primarily on abstract reasoning, scientists began to investigate reality through observation, experiment, and mathematics. They measured the motion of objects, studied the behavior of light, and searched for patterns that could describe the workings of the natural world. This new method did not abandon the philosophical question of reality. Instead, it approached the question from a different direction. Rather than asking only what reality might be in principle, scientists asked how reality behaves. What rules govern motion? Why do objects fall toward the ground? How do planets move across the sky? By answering these questions step by step, they hoped to uncover the hidden structure of the universe itself. And gradually, through careful observation and bold ideas, a new picture of reality began to emerge. It was a universe governed by mathematical patterns and predictable laws, where the movements of planets and falling apples could be described with remarkable precision. In this emerging view, the universe resembled a vast and elegant machine, operating according to rules that could be discovered and understood. The shadows of the cave were beginning to fade. Yet as we will soon see, even this orderly picture of reality would eventually reveal deeper mysteries waiting beneath the surface. For now, it is enough to notice that the question Plato asked long ago still echoes quietly today. Are we seeing reality itself, or only a simplified image of something deeper? The apple remains on the table, calm and familiar. But the story of reality is already beginning to stretch far beyond what our senses alone can reveal. As the centuries passed after Plato, the question of reality slowly began to change its shape. Philosophers had spent generations wondering whether the world we experience is a shadow of something deeper. They debated ideas about truth, appearance, and the nature of existence itself. But eventually a new way of exploring these questions began to emerge. Instead of asking only what reality might be, curious observers began to ask how reality behaves. They watched the sky carefully, tracking the slow motion of the stars and planets. They dropped objects from towers to see how they fell. They rolled balls down slanted ramps and measured how their speed changed. These experiments may sound simple, but they represented a quiet revolution in human thinking. The universe was no longer just a mystery to be contemplated. It became something that could be studied. One of the earliest pioneers of this new approach was an Italian thinker named Galileo. By observing the motion of objects and studying the night sky through a telescope, Galileo began to see patterns hidden within nature. He discovered that the language of those patterns seemed to be mathematics. When objects rolled down a slope, their motion followed precise relationships that could be expressed with numbers. When planets moved through space, their paths could be predicted with careful calculations. Reality, it seemed, was not chaotic or random. It followed rules. A few decades later, these ideas would reach a remarkable turning point through the work of an English scientist named Isaac Newton. Newton lived in the 17th century, a time when the scientific revolution was gathering momentum across Europe. Observers had begun to measure the motions of planets with increasing accuracy, and they were searching for a deeper explanation behind those movements. Newton provided that explanation. In a series of profound insights, he discovered that the same principles governing a falling apple also govern the motion of the moon and the planets. This idea was astonishing. Before Newton, the heavens and the earth were often imagined as separate realms. The stars and planets were thought to follow different rules from the objects we encounter in everyday life. Newton showed that the same laws applied everywhere. An apple falls toward the ground for the same reason that the moon circles the earth. Both motions arise from a universal attraction between masses. What made Newton's discovery even more extraordinary was the precision with which these motions could be described. Using mathematics, Newton developed equations that allowed scientists to calculate how objects move when forces act upon them. But in our quiet exploration tonight, we do not need to focus on the equations themselves. What matters is the vision they created. Newton's work revealed a universe that behaved like a perfectly designed machine. Imagine opening the back of a finely crafted mechanical watch. Inside, you would see gears turning slowly and smoothly, each one connected to the next. Every movement follows from the movement before it. The gears do not move randomly. They obey the structure of the mechanism. Newton's universe looked much the same. Planets move through space like enormous gears in a cosmic clock. Their paths were steady and predictable. If you knew their positions and speeds at a particular moment, you could calculate where they would be hours, days, or even centuries later. This idea became known as the clockwork universe. Reality was no longer a mysterious shadow on the wall of Plato's cave. Instead, it appeared to be a vast and orderly system governed by precise rules. Space provided the stage on which events unfolded. Time ticked forward steadily, like the second hand of a universal clock. Matter moved according to consistent principles that could be discovered, measured, and described. For many thinkers, this vision was deeply reassuring. If the universe followed reliable laws, then human beings could gradually uncover those laws through observation and reasoning. Every discovery would reveal another piece of the great cosmic mechanism. And for more than 2 centuries, Newton's picture of reality worked astonishingly well. Using the principles he discovered, scientists predicted the motion of planets with remarkable accuracy. They explained the paths of comets sweeping through the solar system. Engineers used these ideas to design bridges, machines, and buildings. The clockwork universe seemed not only elegant but reliable. Yet even as Newton's vision spread across the scientific world, subtle questions lingered in the background. The universe appeared predictable, but what exactly was the nature of space and time themselves? Space seemed to stretch endlessly in every direction, providing a silent stage on which the drama of physics unfolded. Time flowed forward at a steady pace, the same for everyone everywhere. But were space and time truly as simple as they appeared? And what exactly was this mysterious attraction that caused masses to pull on one another across empty space? Newton himself admitted that the deeper nature of gravity remained a puzzle. He could describe its effects with extraordinary accuracy, but the underlying cause remained hidden. For a long time, scientists accepted this mystery as a small gap in an otherwise magnificent theory. The universe still appeared orderly and predictable, like a vast mechanical clock whose gears turned smoothly through the ages. Yet the deeper scientists looked into nature, the more hints began to appear that reality might not be quite so simple after all. Strange behaviours of light would soon challenge the old assumptions about space and time. The structure of atoms would reveal deeper layers of matter that did not behave like tiny billiard balls, and eventually new ideas would emerge that transformed our understanding of reality itself. But for now, it is worth pausing for a moment in the calm certainty of Newton's world. In this vision, the universe is a grand machine. Planets glide through the night sky with quiet precision. Apples fall toward the earth in graceful arcs. The ticking of time carries every event forward in steady rhythm. Reality appears orderly, predictable, and beautifully structured. Yet beneath that elegant simplicity, deeper mysteries are already waiting to be discovered. For more than 200 years, Newton's picture of the universe seemed almost unshakable. Objects moved according to clear and predictable rules. Space was an enormous stage stretching endlessly in all directions. Time flowed forward like a steady river, carrying every event along the same universal current. It was a comforting vision. No matter where you were in the universe, time was thought to pass in exactly the same way. A second on Earth was a second on Mars, a second near a distant star, and a second anywhere else in the cosmos. But toward the end of the 19th century, small cracks began to appear in this orderly picture. The trouble started with something that seemed almost too simple to cause problems: light. Light travels astonishingly fast. In fact, it moves so quickly that it can circle the Earth many times in the blink of an eye. Scientists studying light noticed something curious when they tried to measure its speed. No matter how they performed the experiment, the result always appeared to be the same. Even when the source of light was moving, or when the observer was moving, the measured speed of light did not seem to change. At first, this result puzzled researchers. According to Newton's view of motion, speeds should combine in straightforward ways. If you throw a ball forward while riding in a moving train, the ball travels faster relative to the ground than it would if you were standing still. But light did not behave this way. Whether the observer moved toward the light or away from it, the measured speed remained unchanged. This strange result forced scientists to reconsider their assumptions about space and time. One young physicist, Albert Einstein, approached the problem with a bold idea. Instead of assuming that space and time must behave the way we expect, Einstein suggested that the speed of light might be the true constant in nature. If that were the case, then space and time themselves would have to adjust in order to preserve that constant speed. It was a radical thought, but when Einstein followed this idea to its logical conclusion, an entirely new picture of reality emerged. In this new view, space and time were not separate things. They were woven together into a single structure called spacetime. Events in the universe no longer happened within space and time independently. Instead, they unfolded within this combined fabric, where distances and durations could change, depending on how an observer moved. One of the most surprising consequences of this idea involves time itself. In everyday life, we assume that time flows at the same pace for everyone. Two clocks placed side by side will tick together, second by second. But Einstein discovered that when objects move extremely fast, time can pass differently for them. Imagine two identical clocks. One remains quietly on Earth. The other is placed aboard a spacecraft travelling through space at tremendous speed. When the spacecraft returns and the clocks are compared, the clock that travelled through space will have recorded slightly less time. Its seconds passed more slowly. This effect is known as time dilation. The faster an object moves relative to an observer, the more slowly time appears to pass for that object. At the speeds we experience in daily life, the difference is far too small to notice. But for objects moving close to the speed of light, the effect becomes dramatic. Astronauts travelling on extremely fast journeys would age slightly less than the people they left behind. Time, once thought to be a universal river flowing evenly for everyone, turned out to be more like a landscape that changes depending on the path you take through it. This discovery transformed our understanding of reality. Time was no longer absolute. It became something flexible and personal, tied to the motion of each observer. Another consequence of Einstein's ideas concerns the idea of the present moment. In Newton's universe, there was a single universal now. Events happening in different places could be said to occur at the same moment in time. But in Einstein's spacetime, the concept of a universal present becomes more complicated. Two observers moving differently through space may disagree about which distant events are happening at the same time. One observer's now may be another observer's past or future. This does not mean that reality becomes chaotic or inconsistent. Instead, it reveals that time is more subtle than our everyday experience suggests. The universe does not carry a single cosmic clock that everyone shares. Each observer moves along their own path through space-time, carrying their own measure of time with them. This idea can feel strange at first. After all, our daily experience suggests that time is something steady and dependable. Morning becomes afternoon, afternoon becomes evening, and the rhythm of the day feels universal. But beneath that familiar rhythm lies a deeper structure where time and space are intertwined. Imagine space-time as a vast landscape. Each person, each planet, each star traces a path through that landscape. The passage of time is not a separate force pushing everything forward. Instead, it emerges from the way each traveller moves along their path. The apple falling from the tree, the Earth orbiting the Sun, and a distant spaceship crossing the galaxy are all journeys through this four-dimensional terrain. Einstein's insight reshaped physics in profound ways. The steady clockwork universe of Newton gave way to a universe where space and time could stretch, compress, and bend. Yet the story does not end here, because once scientists realized that space and time could change depending on motion, a new question appeared almost immediately. What happens to space and time in the presence of gravity? That question would lead Einstein even deeper into the structure of reality, revealing that gravity itself is not simply a force pulling objects together, but a gentle bending of space-time itself. And with that discovery, the universe would become stranger and more beautiful than anyone had imagined. Newton's vision of the universe was powerful and elegant. For centuries it explained the motion of planets, the falling of apples, and the graceful paths of comets sweeping through the sky. According to that view, gravity was a force, a kind of invisible pull that objects exert on one another across space. The Earth pulls the apple downward, the Sun pulls the Earth into its orbit, every mass attracts every other mass. This picture worked beautifully for everyday motion, and even for the grand movements of the solar system. Yet as scientists began to explore the deeper implications of Einstein's ideas about space and time, they realized that Newton's description could not be the final answer, because if space and time are woven together into a flexible fabric called spacetime, then gravity might not be a simple force acting within that fabric. Instead, gravity might be part of the fabric itself. Einstein approached this question with a remarkable shift in perspective. Rather than imagining gravity as a pull between objects, he asked whether mass might actually change the shape of space-time around it. To picture this idea, imagine a large sheet of flexible fabric stretched tightly across a frame. Now place a heavy ball in the center of the sheet. The weight of the ball causes the fabric to dip downward, creating a gentle curve around it. If you roll a small marble across the sheet, the marble will not travel in a straight line. Instead, it will follow the curved surface created by the heavy ball, circling around it or spiraling inward depending on its path. The marble is not being pulled directly by the ball, it is simply following the shape of the surface beneath it. Einstein suggested that gravity works in a similar way. Mass and energy bend the fabric of space-time. Objects moving through space-time naturally follow the curves that mass creates. In this picture, the Earth does not pull the Moon with an invisible force. Instead, the Earth bends the space-time around it, and the Moon follows the curved path created by that bending. Planets orbit stars because they are travelling along the natural curves in the space-time landscape surrounding those stars. Gravity becomes geometry. The paths of objects are not determined by a force pulling them inward, but by the shape of the cosmic terrain through which they move. This idea may sound abstract, but it produces real and measurable effects. One of the most fascinating consequences involves time itself. Earlier, we discovered that time can pass differently depending on how fast an observer moves. Einstein's theory of gravity revealed that time can also pass differently depending on the strength of gravity. Near a massive object, time flows slightly more slowly. Imagine two identical clocks. One is placed on the surface of the Earth. The other is lifted high above the planet aboard a satellite orbiting far out in space. Because the satellite is farther from Earth's gravity, time passes slightly faster for the clock in orbit than for the clock on the ground. The difference is extremely small, far too tiny to notice in everyday life, but modern instruments can measure it with remarkable precision. In fact, this effect must be taken into account for the navigation satellites that guide modern GPS systems. These satellites carry very accurate clocks. If scientists did not correct for the difference in how time passes in orbit, compared with on Earth's surface, GPS positions would drift by several kilometers each day. In other words, the simple act of navigating across a city quietly depends on Einstein's insight that gravity shapes time itself. The bending of space-time can also influence the path of light. Although light has no mass, it still travels through space-time, and therefore it follows the curves created by gravity. When light passes near a massive object such as a star or a galaxy, its path bends slightly. Astronomers observe this effect when distant galaxies appear distorted or multiplied by the gravitational influence of massive clusters lying between them and Earth. The universe itself sometimes behaves like a vast natural lens. Even more dramatic consequences appear when gravity becomes extremely strong. If a large, enough mass collapses into a small enough region, the curvature of space-time becomes so intense that nothing, not even light, can escape. Such an object is known as a black hole. From the outside, a black hole appears as a region where gravity has folded space-time inwards so steeply that every possible path leads deeper inside. Time itself behaves strangely near these objects. To a distant observer watching from far away, clocks near the edge of a black hole appear to slow almost to a halt. Light leaving that region becomes stretched and dimmer, fading as it climbs out of the deep gravitational well. Yet for someone falling toward the black hole, time would continue to feel normal, at least until reaching the extreme regions where our current understanding of physics begins to break down. These strange effects remind us that gravity is not simply a force pulling things together. It is the shape of space-time itself. Mass and energy sculpt the geometry of the universe, and everything else, planets, light, galaxies, even time, moves along the curves that result. Einstein's theory revealed that reality is far more flexible than Newton imagined. Space can stretch and bend. Time can flow at different rates. And the presence of mass reshapes the very stage on which the universe unfolds. Yet even as scientists were absorbing these revelations about space-time, another revolution was beginning to unfold at a completely different scale. While relativity explored the structure of the cosmos on the larger scales, new experiments were uncovering equally surprising behavior within the smallest building blocks of matter. In that microscopic world, the certainty of classical physics would begin to dissolve. Particles would behave like waves. Events would become governed not by certainty but by probability. And reality itself would grow stranger than anyone had expected. When Einstein reshaped our understanding of space and time, the consequences reached further than many people first realized. At first, relativity simply seemed to describe how clocks and distances behave when objects move quickly or when gravity becomes strong. Time could stretch, space could curve. These ideas were already surprising enough. But as physicists and philosophers thought more deeply about Einstein's space-time, another question quietly emerged. If time is part of a four-dimensional structure, woven together with space into a single fabric, then how should we think about the past and the future? In everyday life, we imagine time as something that flows. The present moment feels like a moving point, gliding steadily from yesterday toward tomorrow. The past seems fixed and complete, while the future appears open and unwritten. But relativity complicates this picture, because once space and time are combined into space-time, events are no longer arranged along a simple universal timeline shared by everyone. Instead, the universe begins to look more like a vast landscape. In this landscape, every event, every falling apple, every turning planet, every quiet thought in the mind has its own position in space-time. All of these events exist as part of the structure. They do not need a moving present moment to bring them into existence. This idea leads to what many physicists call the block universe. Imagine space-time as a giant block containing the entire history of the universe. The birth of stars, the formation of galaxies, the rise of life on Earth, and the distant future of the cosmos all exist as different regions within this block. From this perspective, time does not flow in the way we usually imagine. Instead, the universe simply is. The past, the present, and the future are all part of the same structure, just as different places exist within the landscape of the Earth. A mountain peak does not need to wait for a river valley to appear. Both exist simultaneously within the geography of the planet. In a similar way, the block universe suggests that every moment in time may exist as part of the full geometry of space-time. What we experience as the passage of time might arise from the way our minds move along a particular path through that structure. Physicists often describe this path as a world line. A world line is the trail an object traces through space-time as it moves from one moment to the next. Your entire life, from your first breath to every step you take, every conversation you share, every quiet moment of thought, forms a long, continuous thread through the space-time fabric. The same is true for everything else. The Earth has a world line as it travels around the Sun. A photon of light has a world line as it journeys across the universe. Even galaxies drifting slowly through cosmic space trace their own enormous paths through space-time. All of these threads weave together to form the structure of the block universe. This picture can feel strangely peaceful, but also slightly unsettling. If every moment already exists somewhere within space-time, what happens to the idea of the present? In everyday language, we often imagine that there is a single universal moment happening everywhere at once, a cosmic now shared by the entire universe. Relativity suggests that such a universal present may not exist. Observers moving differently through space can disagree about which distant events occur at the same time. For example, imagine two observers traveling past each other in space at very high speed. Each observer carries their own clock and measures time according to their own motion. When they look out across the universe, they may disagree about whether two distant events are happening simultaneously. One observer might say that a distant star exploded before another galaxy formed a new star. The other observer, moving differently through space-time, might judge those events to occur in the opposite order. Neither observer is wrong. Both descriptions are valid within their own frame of reference. In a universe where space and time are intertwined, the idea of a single shared now becomes less meaningful. Instead, each observer experiences their own sequence of moments along their own world line. This realization leads to profound philosophical questions. If the entire history of the universe already exists within the block structure of space-time, does that mean the future is fixed? Does the path of every event already lie within the cosmic landscape? These questions touch on the ancient tension between determinism and free will. From one perspective, the block universe suggests that the future may already be part of space-time structure. From another perspective, our experience of making choices and shaping events feels undeniably real. Some modern theories even suggest that the block universe might not be the final word. Certain ideas in quantum gravity propose that space-time itself could emerge gradually from deeper processes, meaning that reality might still be unfolding in ways we do not yet fully understand. For now, physicists remain divided on this question. Yet the block universe remains one of the most fascinating interpretations of relativity. It invites us to imagine the universe not as a movie being played frame by frame, but as a vast and complete tapestry woven across space-time. Our lives are threads within that tapestry. We experience the journey moment by moment, step by step, moving along our world lines through the landscape of time. And even though the entire structure may already exist in some deeper sense, the experience of living, of walking along the path, feeling each moment as it arrives, remains deeply meaningful. Because while physics may describe the structure of space-time, our experience unfolds along it like a traveller crossing a wide and mysterious terrain. Yet, even this grand view of the universe is not the end of the story. While relativity revealed the structure of space-time on the largest scales, scientists exploring the microscopic world were beginning to discover something even stranger. At the smallest scales of reality, particles would refuse to behave like tiny solid objects. Instead, they would spread out like waves. Certainty would give way to probability, and the quiet fabric of reality would begin to ripple with possibilities. As scientists were uncovering the elegant structure of space-time through relativity, another revolution was quietly beginning in a very different corner of physics. This revolution did not begin among the stars or galaxies. It began with something much smaller and more familiar: heat and light. At the end of the 19th century, physicists were studying how hot objects glow. If you heat a piece of metal slowly, it begins to shine with a dim red colour. As the temperature rises, the glow becomes brighter and shifts toward orange, then yellow, and eventually a brilliant white. This gradual change in colour puzzled scientists. According to the classical theories of the time, the energy radiated by a hot object should spread smoothly across all possible colours of light. But careful measurements revealed a different pattern. The energy appeared to come in distinct portions. In the year 1900, a German physicist named Max Planck proposed a bold explanation. Instead of assuming that energy flows continuously like water from a stream, he suggested that energy might be emitted in tiny packets. These packets became known as quanta. The word comes from a Latin term meaning how much, referring to the smallest possible amount of energy that could be emitted or absorbed. At first, Planck considered this idea more of a mathematical trick than a fundamental truth. Yet the concept soon began to appear in other surprising places. A few years later, Albert Einstein applied the idea of quanta to light itself. In certain experiments, light striking a metal surface could knock tiny charged particles, called electrons, out of the material. This effect behaved in ways that classical wave theories of light could not explain. Einstein proposed that light sometimes behaves as if it were made of individual particles, each carrying a small packet of energy. Today we call these particles photons. With this proposal, light revealed a curious dual nature. In many situations, it spreads through space like a wave, producing patterns of interference and diffraction much like ripples on water. Yet in other situations, it behaves like a stream of tiny particles delivering energy in discrete bursts. Light, it seemed, was not entirely a wave and not entirely a particle. It was both. This strange dual behaviour puzzled physicists for years, but the mystery deepened even further when scientists turned their attention to matter itself. In the early 20th century, a young French physicist named Louis de Broglie suggested something remarkable. If light, which had long been understood as a wave, could sometimes behave like a particle, perhaps the reverse might also be true. Perhaps particles of matter could behave like waves. It was a radical idea. We usually imagine particles as tiny solid objects, like miniature grains of sand or microscopic billiard balls. They move through space along definite paths, colliding and bouncing in predictable ways. But de Broglie proposed that every particle might also have a wave-like aspect. In this view, an electron moving through space would not simply follow a single narrow trajectory. Instead, it would spread out like a wave, its presence distributed across a region of space. Experiments soon confirmed this astonishing prediction. When beams of electrons were directed through thin crystals or narrow openings, they produced interference patterns, delicate bands of light and dark that could only be explained if the electrons behaved like waves. The same patterns appear when waves of water pass through a pair of openings in a barrier and spread across a pond. Instead of travelling along a single straight path, the electrons seem to ripple outward and interact with themselves, forming patterns of peaks and troughs. The old image of tiny solid particles moving along simple trajectories began to dissolve. At the microscopic scale, reality behaved differently. Matter itself possessed a wave-like character. The implications of this discovery were profound. If particles can behave like waves, then the familiar picture of objects occupying precise locations at all times becomes less certain. An electron inside an atom does not orbit the nucleus like a planet circling the sun. Instead, it forms a kind of standing wave around the nucleus, a pattern that describes where the electron is most likely to be found. the atom becomes less like a miniature solar system and more like a vibrating structure of probability. These wave-like patterns help explain why atoms are stable. Instead of spiraling inward toward the nucleus, electrons occupy specific energy levels that correspond to stable wave patterns. Much like the notes produced by a violin string, only certain vibrations are allowed. When an electron shifts from one pattern to another, it absorbs or releases energy in discrete packets, those same quanta first proposed by Planck. In this emerging picture, the microscopic world is no longer built from rigid particles following precise paths. Instead, it resembles a delicate interplay of waves and possibilities. A particle can behave like a wave. A wave can sometimes appear as a particle. Reality at the smallest scale becomes fluid and dynamic, more like ripples on a pond than solid grains of matter. And yet, in our everyday lives, we do not notice this wave-like behavior. A baseball does not spread across the field like a ripple. A grain of sand does not pass through two doorways at once. The wave nature of matter becomes visible only for extremely small objects, particles so tiny that their wave patterns are not overwhelmed by interactions with the surrounding world. Still, these discoveries mark the beginning of a profound transformation in physics. The classical certainty of Newton's universe had already been reshaped by relativity. Now, quantum theory was revealing that the microscopic world followed its own set of rules in which waves and particles blend together in ways that challenge our ordinary intuitions. And as scientists explored this strange new domain more deeply, they would encounter an even more surprising idea. At the smaller scales of reality, events might not be determined with absolute certainty. Instead, the universe might unfold through patterns of probability. When the first explorers of quantum physics began studying the strange wave-like behavior of particles, they quickly realized something even more surprising. If particles behave like waves, then perhaps the universe does not always determine exact outcomes in the way classical physics once assumed. Instead, the microscopic world might unfold through possibilities. One of the key figures who helped clarify this idea was a physicist named Max Born. He proposed that the wave associated with a particle does not represent the particle itself in a simple physical sense. Instead, the wave describes the probability of finding the particle in different places. To understand this idea, imagine that you are trying to locate a small marble inside a room. In the classical world, the marble has a precise position at every moment. Even if you cannot see it immediately, it exists at a definite point in space. In quantum physics, the situation is more subtle. Before a measurement is made, the particle does not occupy a single sharply defined location. Instead, it exists as a spread of possibilities, a cloud describing where the particle might appear when observed. Physicists use a mathematical description called the wave function to represent this cloud, but in our quiet exploration tonight, it is helpful to imagine something simpler. Picture a soft mist filling part of a room. The mist is not concentrated at one point. Instead, it spreads gently through the space, with some areas thicker than others. If you are asked whether mist is most likely to appear when a beam of light passes through it, you would say that it is most likely to appear where the mist is densest. The quantum wave behaves in a similar way. It tells us where a particle is more likely or less likely to be found when we observe it. This does not mean that the particle itself is physically smeared like fog. Rather, it means that the information we have about its location exists in the form of probabilities. The universe at the smaller scale seems to describe possibilities before it settles on specific outcomes. This insight leads to one of the most famous features of quantum physics, uncertainty. In everyday life, we expect that if we know enough information about an object, its position and speed, for example, we should be able to predict exactly what it will do next. But quantum mechanics reveals a fundamental limit to this certainty. The more precisely we know a particle's position, the less precisely we can know its motion. And the more precisely we know its motion, the less precisely we can know its position. This is not simply a problem with our instruments, it is built into the structure of reality itself. At the smallest scales, nature does not allow perfect knowledge of both properties at once. Instead of sharp points and exact trajectories, the microscopic world becomes a shifting landscape of probabilities. Yet even with this uncertainty, quantum physics remains astonishingly successful at predicting experimental results. It tells us, with remarkable accuracy, the likelihood of different outcomes. And when many particles are involved, these probabilities combine in ways that create the stable world we experience. To see why this matters, imagine flipping a single coin. Before it lands, the outcome is uncertain. It could fall as heads or tails, but if you flip thousands of coins, patterns begin to emerge. Roughly half will land one way and half the other. The randomness of individual events blends into predictable patterns when large numbers are involved. Something similar happens in the quantum world. Individual particles behave in uncertain ways, but when enormous numbers of them interact, inside atoms, molecules, and everyday objects, the overall result becomes stable and reliable. This is why tables feel solid and apples do not suddenly vanish. Quantum uncertainty is most visible in the microscopic realm. Another example of this unusual behavior appears in a phenomenon called tunneling. In the classical world, if a ball rolls toward a hill that is too high, the ball simply stops and rolls back. But in the quantum world, particles behave partly like waves, and waves have the curious ability to leak through barriers. Imagine a gentle ripple moving across the surface of water. When it reaches a narrow wall with a small gap, part of the ripple may appear on the other side. In quantum physics, particles sometimes behave similarly. Even if a barrier seems too high for a particle to cross in the classical sense, there is still a small probability that the particle's wave-like nature allows it to appear on the other side. This effect is known as quantum tunneling. It sounds almost magical, yet it occurs constantly in nature. Tunneling plays an essential role in nuclear reactions inside stars, allowing atomic nuclei to combine and release energy that eventually reaches us as sunlight. It also powers many modern technologies, including certain types of electronic devices that rely on electrons slipping through barriers in precisely controlled ways. These examples remind us that the microscopic world does not always follow the tidy rules we once expected. Particles can behave like waves. Locations become clouds of possibility. Events unfold through probabilities rather than certainty. And yet, from this subtle and uncertain foundation, the familiar world of everyday experience emerges with remarkable stability. The apple on the table still feels solid. The Earth continues to orbit the Sun. The laws of physics remain dependable. Beneath that reliability, however, the quantum world quietly hums with possibilities. And as physicists explored this mysterious realm more deeply, they discovered something even stranger. Particles separated by enormous distances could become connected in ways that defied classical intuition. A measurement made in one place could be linked to outcomes in another, as though the universe itself were woven together more tightly than ordinary space might suggest. This phenomenon would become known as entanglement, and it would challenge our understanding of reality more deeply than almost anything that came before. As physicists continued exploring the strange world of quantum mechanics, they gradually realized that the theory contained an even deeper surprise. Particles did not merely behave like waves or clouds of probability. In some circumstances, they could become linked together in ways that seemed to transcend ordinary distance. This phenomenon became known as quantum entanglement. To understand why entanglement puzzled scientists so deeply, it helps to remember that classical physics assumed a very simple rule about the universe. Objects influence one another through direct interaction. If two things are separated by a large distance, any effect travelling between them must move through space from one place to the other. Information cannot leap instantly across the cosmos. This idea feels natural because it matches our everyday experience. If you ring a bell in one room, someone in a distant room hears it only after the sound waves travel through the air. If you send a letter across the world, it takes time for the message to arrive. Distance usually means delay. But quantum physics began to suggest that the universe might not always follow this expectation. The story began with a thought experiment proposed by Albert Einstein and two colleagues, Boris Podolsky and Nathan Rosen. Together they considered a pair of particles created in such a way that their properties were connected. Imagine, for instance, that two particles are produced together and then fly apart in opposite directions. Because of the way they were created, certain properties of the pair must remain balanced. If one particle later shows a particular value when measured, the other particle must show the opposite value. For example, imagine two tiny spinning coins produced together, so that one must land heads whenever the other lands tails. The two coins travel far away from each other, perhaps to opposite sides of the galaxy. According to the logic of entanglement, measuring the first coin instantly tells you the state of the second one. Even though the particles are separated by enormous distances, their properties remain linked. Einstein found this idea troubling. He believed that the universe should obey clear rules about locality, that events occurring in one place should not instantly influence events far away. He famously referred to entanglement as spooky action at a distance, suggesting that something must be missing from the theory. Perhaps, Einstein suggested, the particles carried hidden information from the moment they were created, secret instructions that determined their behavior later on. If such hidden variables existed, the universe could remain orderly and local while still producing the patterns predicted by quantum theory. For several decades, this debate remained unresolved. Then, in the 1960s, a physicist named John Bell developed a clever way to test the idea. Bell realized that if hidden variables governed the behavior of entangled particles, certain statistical limits should appear in the results of carefully designed experiments. But if quantum mechanics were correct in its description of entanglement, those limits would be violated. This insight led to a series of delicate experiments performed over many years. Scientists generated pairs of entangled particles and sent them in different directions toward distant detectors. By measuring the properties of each particle in many different orientations, they could compare the results and look for the patterns predicted by Bell's reasoning. Again and again, the experiments revealed the same conclusion. Nature behaved exactly as quantum theory predicted. The correlations between entangled particles were stronger than any explanation based on hidden variables could allow. In other words, the universe itself seemed to contain a form of connection that did not fit neatly into classical ideas about locality. This does not mean that information travels instantly from one particle to the other. Entanglement cannot be used to send messages faster than light. The results of measurements remain unpredictable until they are compared afterward. Yet the correlations themselves appear real. Two particles that share an entangled state behave like parts of a single system, even when separated by vast distances. It is as though the pair forms one extended object stretching across space. To visualize this idea, imagine two musicians playing a melody together. Even if they move to opposite sides of a city, the notes they produce remain linked by the structure of the music they share. Each note played by one musician fits perfectly with the note played by the other. The connection is not carried by a signal traveling between them in that moment. It comes from the deeper pattern they both belong to. In a similar way, entangled particles appear to share a deeper pattern embedded in the quantum description of reality. This realization has led some physicists to wonder whether the universe might be more interconnected than ordinary space suggests. Perhaps space itself emerges from deeper relationships between quantum systems. Some modern theories even explore the possibility that entanglement helps weave the fabric of space-time together. In such views, the connections revealed by quantum experiments are not strange exceptions. They may be clues pointing toward the underlying architecture of reality. What we perceive as separate objects scattered across space might, at a deeper level, be threads within a single cosmic tapestry. Each thread moves along its own path, yet the pattern connecting them remains hidden beneath the surface. For now, entanglement remains one of the most fascinating features of quantum physics. It reminds us that the universe may not be composed of isolated pieces interacting across empty space. Instead, reality may be structured through relationships, quiet links that connect distant parts of the cosmos in subtle ways. And as scientists continued to explore these connections, they began to uncover an even more fundamental layer beneath the particles themselves. Because according to modern physics, particles might not be the deepest ingredients of reality at all. Beneath them lies something more continuous, something that fills all of space like an invisible ocean. Physicists call these deeper ingredients quantum fields. For a long time, scientists imagined that the universe was built from tiny solid pieces. Atoms were once thought to be the smallest building blocks of matter. Later, physicists discovered that atoms themselves contain smaller components, electrons orbiting around dense centers made of protons and neutrons. Then those particles were found to contain even smaller ingredients called quarks. At first, each discovery seemed to reveal another layer of miniature objects hidden within the previous one. It was natural to imagine that if we continued looking deeper, we would eventually reach the smallest particles of all, the final grains of matter from which everything else is built. But as the 20th century progressed, physicists began to realize that reality might be structured in a different way. Particles might not be the most fundamental things in the universe. Instead, something else may lie beneath them. That deeper level is described by what physicists call quantum fields. To understand this idea, imagine the surface of a calm ocean. Even when the water appears smooth, the ocean is still present everywhere across its surface. If a disturbance occurs, perhaps a gust of wind or a falling drop of rain, waves form and ripple outward. The waves are not separate from the ocean. They are patterns of motion within the water itself. Quantum field theory suggests that something similar happens throughout the universe. Instead of empty space containing isolated particles, space is filled with fields that extend everywhere. These fields are present at every point in the cosmos, even in regions where no particles appear to exist. When a field vibrates in a particular way, the vibration shows up as a particle. In this view, an electron is not a tiny solid object travelling through space like a miniature marble. It is a small ripple in the electron field. A photon, the particle of light, is a ripple in the electromagnetic field. Quarks arise from vibrations in their own fields, and other particles correspond to their own distinct patterns of motion. The universe becomes less like a collection of tiny objects and more like an enormous sea of interacting fields. Particles are simply the visible waves that appear on that sea. This shift in perspective helps explain many puzzling features of the quantum world. For example, particles of the same type are perfectly identical. Every electron in the universe has exactly the same mass and charge. In the classical picture of tiny objects, this perfect similarity would be difficult to explain. But in the field picture, it becomes natural. All electrons are simply excitations of the same underlying field. Just as every wave on the ocean follows the same basic rules of water, every electron follows the properties of the electron field. Quantum field theory also explains how forces operate in nature. In classical physics, forces were imagined as invisible pulls or pushes between objects. But in the language of fields, forces arise from interactions between different fields. When two electrons repel each other, the interaction is carried by disturbances in the electromagnetic field. These disturbances appear as particles of light, photons, exchanged between the electrons. In other words, the forces we observe can be understood as conversations between fields. The electromagnetic field communicates with the electron field. Other fields carry the interactions responsible for nuclear forces within atomic nuclei. Together, these interactions form a framework known as the Standard Model of Particle Physics. This model describes the known particles and their interactions with extraordinary accuracy. Experiments conducted in particle accelerators around the world have confirmed its predictions again and again. Yet one of the most fascinating features of this framework involves a field that fills the entire universe almost silently. This is the Higgs field. For many years, physicists struggled to understand why certain particles possess mass, while others remain massless. Light particles, such as photons, travel freely at the cosmic speed limit, but particles like electrons and quarks have measurable mass, giving matter its weight and solidity. The Higgs field provides part of the explanation. According to modern theory, the Higgs field permeates all of space. When certain particles move through this field, they interact with it in ways that give rise to mass. You might imagine this interaction as something like a swimmer moving through water. Some swimmers glide easily, experiencing little resistance. Others encounter stronger interactions with the water, slowing them down. In a loose sense, particles that interact more strongly with the Higgs field behave as though they have greater mass. In 2012, scientists working at the Large Hadron Collider near Geneva observed a new particle consistent with the predicted ripple of the Higgs field. This discovery provided strong confirmation of the field-based picture of matter. By this point, the old image of the universe made from tiny solid building blocks had almost completely dissolved. Reality appeared instead as a dynamic network of fields stretching throughout space. Particles were no longer the deepest ingredients of nature. They were simply patterns, temporary vibrations arising from the underlying fields, and those fields themselves interact, merge, and transform in ways that create the complex structures we observe around us. From this perspective, the apple resting on the table is not a simple object. It is a stable pattern formed by countless interacting fields. The electrons within it are ripples in one field. The quarks within its atomic nuclei are ripples in others. Forces between them arise from further interactions between fields that extend throughout space. Even empty space is not truly empty. Fields remain present everywhere, quietly fluctuating with tiny quantum motions. The universe becomes something like an immense symphony played on invisible instruments. Each field contributes its own tone, its own rhythm of vibration, and the particles we observe are the notes emerging from that cosmic music. Yet even this remarkable picture may not be the final layer of reality. Because as physicists studied the mathematical structure of these fields more deeply, they began to notice something else guiding their behaviour. Beneath the particles and fields, there seemed to be hidden patterns of symmetry, subtle rules shaping how the universe organises itself. These symmetries would soon reveal another elegant layer in the architecture of reality. By the time physicists began to understand the universe in terms of quantum fields, a new question quietly emerged. Why do these fields behave according to such precise rules? Why do particles carry the properties they do? Mass, charge, spin. And why are certain interactions allowed while others never occur? When scientists studied the equations describing these fields, they noticed something remarkable. Again and again, the laws of nature seem to possess a special kind of balance. This balance is known as symmetry. In everyday language, symmetry means that something remains unchanged when it is transformed in a certain way. Imagine placing a beautifully shaped vase on a table. If you rotate the vase slowly in a circle, the shape may appear exactly the same from every direction. Turning it does not change its appearance. The vase is symmetrical under rotation. Symmetry appears everywhere in nature. Snowflakes form delicate patterns that repeat as they turn. Honeycombs grow in hexagonal shapes that tile together perfectly. Even the human body shows a kind of left-right symmetry, with arms and legs arranged as mirror images. But the symmetries physicists study are often more abstract. Instead of shapes or patterns, they involve the deep rules governing the universe. One of the most profound discoveries about symmetry came from a brilliant mathematician named Emmy Noether in the early 20th century. Noether noticed that whenever a physical system possesses a certain symmetry, a corresponding quantity must remain conserved. A conservation law means that a particular property of a system does not change as time passes. For example, consider energy. Energy can change form. It may move from motion to heat, or from electricity to light. But the total amount of energy in a closed system remains constant. Noether showed that this conservation of energy arises from a symmetry of time itself. If the laws of physics remain the same today as they were yesterday and will be tomorrow, then energy must be conserved. Similarly, the conservation of momentum arises from the symmetry of space. If the laws of physics are the same everywhere, whether an experiment is performed here or 1,000 kilometers away, then momentum must remain conserved. These connections revealed that the universe possesses a kind of hidden rule book. Symmetry is not merely aesthetic, it is woven into the foundations of physical law. The deep structure of reality reflects patterns of invariance, rules that remain unchanged under certain transformations. Quantum field theory embraces this idea of symmetry even more strongly. The interactions between fields follow patterns determined by underlying symmetries. These symmetries dictate how particles behave and which interactions are possible. In many ways, the universe resembles a vast choreography. Each field moves according to a set of rules that maintain harmony within the system. Yet an even more fascinating twist appears when symmetry is not perfect. Sometimes symmetry breaks. To picture this idea, imagine a perfectly balanced pencil standing upright on its tip. In theory, the pencil could fall in any direction. Every direction around it is equally possible. The situation is perfectly symmetrical. But once the pencil begins to fall, the symmetry disappears. The pencil chooses a particular direction, and that direction becomes part of reality. Physicists call this phenomenon broken symmetry. The underlying rules remain symmetrical, but the state that actually emerges chooses one possibility over others. This idea plays a crucial role in the history of the universe. Shortly after the Big Bang, the universe may have been extremely symmetrical. The fundamental forces of nature might once have been unified in ways that appear very different from the forces we observe today. As the universe expanded and cooled, certain symmetries broke. Like the falling pencil choosing a direction, the cosmos settled into particular patterns. These broken symmetries help shape the physical laws and particles that now exist. One of the most intriguing examples involves matter and antimatter. According to the basic laws of particle physics, matter and antimatter should be produced in nearly equal amounts. When particles meet their antiparticles, they can annihilate one another, releasing energy. If perfect symmetry had prevailed, the early universe might have produced equal quantities of both. In that case, Matter and antimatter would have destroyed each other almost completely, leaving behind little more than radiation. Yet our universe clearly contains far more matter than antimatter. Stars, planets, and living beings all depend on this imbalance. Somewhere in the early moments of cosmic history, a slight asymmetry emerged, a tiny preference for matter over antimatter. That small difference allowed a fraction of matter to survive the great annihilation that followed. From that surviving matter came galaxies, stars, and eventually life. The symmetry of the early universe cracked just slightly, and from that crack, the entire structure of the cosmos grew. This realization highlights something deeply beautiful about the laws of nature. Reality is guided by elegant patterns of symmetry, yet it also depends on subtle imperfections. The universe is orderly but not perfectly balanced. It is as though a mirror reflecting perfect symmetry contains one tiny flaw, a small deviation that allows complexity to unfold. Without that deviation, the universe might have remained a smooth, featureless sea of energy. Instead, the broken symmetry opened the door to structure, diversity, and the emergence of life itself. From this perspective, the cosmos becomes something like a dance between order and variation. Symmetry provides the rhythm. Broken, symmetry introduces new movements. Together they shape the evolving choreography of the universe. Yet as physicists continued exploring the deeper symmetries of nature, another possibility began to appear. Perhaps even space-time itself, the stage on which this dance unfolds, is not fundamental. Perhaps space and time emerge from something even deeper. If that is true, then the fabric of reality may be woven from structures we're only beginning to glimpse. For much of modern physics, space-time has played the role of the great stage on which the drama of the universe unfolds. Einstein taught us that space and time are not rigid and separate things. Instead, they form a flexible fabric, space-time, that bends in response to mass and energy. Planets move along its curves, light follows its subtle slopes, and gravity itself emerges from its shape. This picture has been extraordinarily successful. General relativity explains the motion of planets, the bending of light near massive objects, and even the expansion of the universe. Yet when physicists try to combine Einstein's description of space-time with the strange rules of quantum mechanics, something curious happens. The two theories do not easily fit together. Quantum physics describes a world of probabilities, fluctuations, and discrete events. Space-time in Einstein's theory, however, is smooth and continuous, like an unbroken sheet of fabric. When scientists attempt to apply quantum principles to space-time itself, that smooth fabric begins to look unstable. This tension has led physicists to wonder whether space-time might not be fundamental after all. Perhaps space and time themselves emerge from something deeper. One idea exploring this possibility is known as loop quantum gravity. In this approach, space-time is not infinitely smooth. Instead, it may be woven from extremely tiny building blocks, loops so small that they lie far beyond the reach of any current experiment. You might imagine these loops as threads forming a piece of cloth. From a distance, the cloth appears smooth and continuous. But when you look very closely, you discover that it is made from countless interwoven strands. Similarly, loop quantum gravity suggests that space itself may be built from discrete pieces connected together in intricate networks. If this is true, then space is not an endless continuum. It is more like a finely woven fabric composed of extremely small units. Another idea takes a different approach. In string theory, the most fundamental ingredients of the universe are not point-like particles at all. Instead, they are tiny, vibrating strings. These strings are unimaginably small, so small that they would appear point-like even in the most powerful particle accelerators we can currently build. But according to the theory, the different ways these strings vibrate give rise to the particles we observe. One vibration might appear as an electron, another vibration might behave like a photon, another might correspond to a particle that carries the force of gravity. Just as different notes arise from different vibrations of a musical string, the diversity of particles could emerge from different patterns of vibration in these fundamental strings. One of the intriguing consequences of string theory is the possibility that the universe may contain additional spatial dimensions beyond the three we experience in everyday life. These extra dimensions would be curled up at extremely small scales, hidden from ordinary observation. You might imagine a garden hose lying across the ground. From far away, the hose appears as a simple one-dimensional line stretching through space. But if you move closer, you discover that the hose has a circular shape as well, another dimension wrapped tightly around the first. Similarly, string theory suggests that the fabric of the universe might contain hidden dimensions curled up so tightly that we cannot easily perceive them. Perhaps the most surprising idea to emerge from modern theoretical physics is known as the holographic principle. This concept proposes that the information describing a region of space might actually be encoded on a lower dimensional boundary surrounding that region. To picture this idea, imagine a hologram. A holographic image appears three-dimensional when you look at it. You can walk around it and see depth and structure. Yet the information creating that image is stored on a flat surface. In a similar way, the holographic principle suggests that the physics occurring within a volume of space might be fully described by information encoded on its boundary. In certain theoretical models, a universe with gravity inside it can be equivalent to a different description that lives on a lower dimensional surface without gravity. This strange relationship hints that space-time itself might emerge from deeper patterns of information. From this perspective, the three-dimensional world we experience could arise from a more fundamental description written in a different number of dimensions. Reality begins to resemble a shadow cast by something more fundamental. Just as a shadow on a wall carries the outline of an object we cannot directly see, the space-time around us might reflect deeper structures hidden beneath its surface. These ideas remain speculative. Physicists continue to test and debate them, searching for evidence that might reveal which path leads closer to the truth. Yet even the possibility that space-time is not fundamental has profound implications. It suggests that the familiar stage of reality, space stretching around us and time flowing forward, might itself be an emergent phenomenon, arising from more abstract relationships. The universe may not be built from objects sitting within space. Instead, space itself might grow from the underlying connections between more basic elements of reality. As this realization began to take shape, some physicists started to ask an even more radical question. If space-time may emerge from deeper patterns, what exactly are those patterns made of? Some thinkers propose that the ultimate foundation of reality might not be matter or fields at all. Perhaps the deepest layer of the universe is information itself, patterns, relationships, structures that exist not as objects but as rules, describing how things can change and interact. And from those patterns, the entire visible world may arise. As physicists continued to explore the deepest layers of the universe, a curious shift in perspective began to appear. For centuries, the search for reality had focused on substances. First came solid matter, atoms and particles imagined as the ultimate building blocks of nature. Later came fields, continuous structures filling space, whose vibrations create the particles we observe. But some scientists began to wonder whether even fields might not be the most fundamental ingredients of reality. perhaps something more abstract lies beneath them. One of the most influential thinkers to explore this idea was the American physicist John Archibald Wheeler. Wheeler proposed a simple yet profound phrase that captured his view of the universe: it from bit. In this phrase, the word it represents the physical things we observe: particles, fields, stars, galaxies, and even spacetime itself. The word bit refers to the smallest unit of information, the kind of binary choice used in digital systems: yes or no, 0 or 1. Wheeler suggested that physical reality might ultimately arise from information. Instead of matter producing information, information itself might give rise to matter. To imagine what this means, consider a piece of music. The melody you hear from a violin or piano is made of sound waves travelling through the air. Yet before the music is played, it can exist as a pattern written on a sheet of paper. The notes themselves are not the sound. They are instructions describing how the sound should unfold. In a similar way, the physical universe might be the manifestation of deeper informational patterns. Particles, forces, and fields could arise from the way information is structured and processed within the fabric of reality. Some physicists explore this idea through the study of quantum information. Quantum systems can store and transmit information in ways that differ dramatically from classical systems. Entangled particles, for example, behave as if they share information across space in subtle ways. In certain modern theories, the geometry of space-time itself may emerge from patterns of quantum information connecting different regions of the universe. From this perspective, reality begins to resemble a network of relationships. The physical world becomes less like a collection of objects and more like a web of information flows. These ideas naturally lead to another possibility that has captured both scientific and philosophical imagination. If reality is built from information, could the universe itself resemble a vast computation? This line of thought sometimes appears in discussions of the simulation hypothesis. The simulation hypothesis suggests that the universe we experience might be the result of a sophisticated computational process. In such a scenario, the physical laws we observe could function like the rules of a simulation, guidelines governing how information evolves from one moment to the next. To picture this idea, imagine a detailed virtual world generated by a computer. Within that world, landscapes, objects, and characters appear solid and real to the inhabitants of the simulation. Yet their existence ultimately arises from patterns of information processed by underlying hardware. Some philosophers and scientists have wondered whether something similar could be true of our own universe. However, it is important to approach this idea carefully. The simulation hypothesis remains speculative. It is not a proven scientific theory, but rather a philosophical possibility raised by the growing power of computational models and our increasing understanding of information. Whether or not the universe resembles a simulation, the idea highlights an intriguing point. Reality might not depend on solid substance in the way we once imagined. Instead, patterns of information and rules of transformation could play a deeper role in shaping the world. Another proposal extends this idea even further. The physicist Max Tegmark has suggested that the universe might be fundamentally mathematical. According to this view, reality itself could be a mathematical structure. In mathematics, structures exist as relationships between elements defined by precise rules. These structures do not require physical matter to exist. For example, the properties of a geometric shape remain true regardless of whether the shape is drawn on paper. Tegmark's idea proposes that the universe might correspond to one such mathematical structure. The physical laws we discover, those describing fields, particles, and spacetime, could be reflections of deeper mathematical relationships. In this view, reality is not made of physical stuff in the traditional sense. Instead, the universe exists as a consistent pattern within the vast landscape of mathematical possibilities. These ideas may sound abstract, even dreamlike, yet they emerge from serious attempts to understand why the universe behaves according to such precise and elegant laws. Why does nature follow mathematical rules so accurately? Why do simple equations capture the motion of planets and the interactions of particles with such extraordinary precision? Perhaps mathematics is not merely a language describing the universe. Perhaps it is the underlying structure from which the universe emerges. Of course, these questions remain open. Physics continues to search for experimental evidence that might confirm or challenge these possibilities. The deeper we look, the more the nature of reality appears to shift from solid objects toward patterns, relationships, and information. The universe may be less like a pile of bricks and more like a complex piece of music, an evolving composition guided by hidden rules. Yet amid these profound speculations, one important truth remains. All of these theories arise from a remarkable source. They arise from conscious minds asking questions about the world. The universe has produced beings capable of reflecting on its nature, exploring its laws, and wondering about its deepest structure. Which brings us to one final and intimate question. If reality may ultimately be built from patterns, information, or mathematical relationships, what role does consciousness play within that reality? What is the nature of the mind that is asking these questions in the first place? After travelling across the vast scales of the universe, through space-time, quantum fields, and the deep structure of reality, it is natural to return to a quieter question. Not a question about galaxies or particles, but about you, because the universe does not only exist out there among the stars, it also exists here in the experience of being a conscious observer within it. And once we begin thinking about reality in terms of patterns, structures, and changing processes, a curious puzzle appears much closer to home. What exactly makes you the same person over time? At first glance, the answer seems obvious. You feel like the same individual you were yesterday and the same person who woke up this morning. Your memories connect one moment to the next, forming a continuous story of your life. But when we examine the physical side of this question, the picture becomes more subtle. A famous thought experiment from ancient philosophy helps illustrate the puzzle. It is known as the ship of Theseus. Imagine a wooden ship that sails across the sea for many years. Over time, parts of the ship begin to wear out. One by one, the old wooden planks are replaced with new ones. Eventually, every plank, every beam, and every nail has been replaced. The question is simple, but surprisingly difficult. Is it still the same ship? Some people say yes. The ship has remained the same vessel throughout its journey, even though its parts were gradually replaced. Others say no. Once every piece has changed, the original ship no longer exists. This thought experiment becomes even more intriguing when we apply it to the human body. Unlike a wooden ship, the human body is constantly renewing itself. Cells grow, divide, and die. New cells take their place. The skin that covers your body slowly renews itself over the course of weeks. Blood cells circulate for only a few months before being replaced. Even bones, which feel so solid and permanent, quietly rebuild themselves over the years through a slow process of renewal. Scientists estimate that most of the cells in the human body are replaced over time. The process is gradual and continuous, happening quietly beneath our awareness. In a sense, the physical matter making up your body today is not exactly the same matter that formed your body years ago. And yet, despite these changes, you still experience yourself as the same person. Your memories connect the past to the present. Your personality carries familiar patterns of thought and feeling. Your sense of identity flows smoothly from one day to the next. This suggests that the essence of identity may not lie in the specific pieces of matter that compose us. Instead, it may lie in patterns. Imagine a river flowing through a landscape. If you return to the river a year later, the water you see is not the same water that flowed there before. Every drop has moved onward, replaced by new water arriving from upstream. Yet we still recognize the river as the same river. Its shape, its path through the land, and the pattern of its flow remain, consistent even as the individual molecules of water change. Identity may work in a similar way. The body is like the riverbed guiding the flow of biological processes. Cells come and go, molecules are replaced, and energy moves constantly through the system. But the overall pattern remains stable enough that we experience continuity. Another helpful image is that of a piece of music. A melody can be performed by different musicians at different times. The instruments may change, the performers may vary, and the air carrying the sound waves is never the same. Yet the melody remains recognizable. The pattern of notes preserves the identity of the song. Similarly, the identity of a person may be less about the specific atoms in the body and more about the patterns those atoms form. Your memories, neural connections, habits of thought, and emotional responses create a dynamic structure that persists even as its physical components slowly shift. From this perspective, the self becomes a process rather than a fixed object. You're not a static collection of matter. You're an ongoing pattern unfolding through time. Your life is a continuous story written through changing experiences and evolving memories. Each moment grows out of the previous one, forming a thread of identity that stretches across your personal timeline. This idea connects naturally to the broader themes we have explored throughout this journey. Earlier we discovered that particles arise from fields and that the universe may ultimately be shaped by patterns of information and relationships. Now we see that identity itself may follow a similar principle. The self may not be a solid, unchanging core hidden within the body. Instead, it may be a living pattern, an organized flow of matter, energy, and information, a process unfolding through time. And within that process arises one of the most remarkable features of the universe: awareness. The ability to experience the world, to reflect on it, and to ask questions about its nature, which leads us gently toward the final mystery. Because if identity is a pattern, and the brain is a network of cells constantly exchanging signals, how does consciousness emerge from that activity? How does the universe give rise to the experience of being aware? Throughout this journey, we have travelled from the ordinary to the extraordinary. We began with something simple, an apple resting quietly on a table. From there, we looked closer and discovered layers beneath the familiar surface. Cells gave way to molecules, molecules to atoms, atoms to particles, and particles to the deeper rhythms of quantum fields. Space and time revealed themselves as flexible structures. Fields vibrated through the universe like notes in a cosmic symphony. Information and mathematical patterns appeared as possible foundations beneath the physical world. And yet, through all of this exploration, one remarkable feature has remained present: the ability to experience it. The universe is not only a structure of matter and fields, it is also something that can be observed, reflected upon, and wondered about. That experience arises from consciousness. Inside the human brain, billions of nerve cells form a vast network of connections. Each cell communicates with others through small electrical signals and chemical exchanges. These signals move along intricate pathways, forming patterns that shift from moment to moment. From the outside, the brain appears as a biological organ composed of cells, proteins, and flowing chemicals. But from the inside, those patterns of activity give rise to thoughts, memories, emotions, and awareness. Some scientists believe that consciousness emerges naturally from this complex activity. In this view, awareness is not located in a single place within the brain. Instead, it arises from the interaction of many processes working together, much like the flame of a candle emerging from countless tiny, chemical reactions occurring within the burning wick. No single spark creates the flame, but together the sparks sustain the light. Similarly, consciousness may emerge from the coordinated activity of vast networks of neurons. As signals travel through the brain, patterns of information integrate and interact, producing the rich experience we call awareness. This perspective is often described as emergence. An emergent property is something that arises from a system when many smaller parts interact. Individual water molecules, for example, do not possess the property we call a wave, but when many molecules move together across the ocean's surface, waves appear. In a similar way, consciousness might emerge from the collective activity of the brain's networks. Yet despite decades of research, the precise nature of consciousness remains one of the deepest mysteries in science. We can observe the brain's activity with remarkable tools. We can measure electrical patterns and map networks of neurons. But explaining how physical processes give rise to subjective experience remains a profound challenge. Why does the brain produce the feeling of being aware? Why does information processing sometimes come with an inner perspective, a sense of what it is like to experience the world? These questions have inspired many different philosophical ideas. Some thinkers explore the possibility that consciousness might be a fundamental feature of reality itself. This view is sometimes called panpsychism. According to this idea, the basic ingredients of the universe might possess extremely simple forms of awareness. Complex minds, such as human consciousness, could arise when these elementary forms combine in intricate ways. Other philosophers remain cautious about such proposals, suggesting that consciousness may eventually be explained through deeper discoveries in neuroscience and physics. For now, the question remains open, as physicists have explored the boundaries of cosmology and statistical mechanics. They have also encountered unusual thought experiments that highlight how mysterious consciousness can be. One such idea involves what are sometimes called Boltzmann brains. The concept arises from thinking about an extremely large universe lasting for an immense span of time. In such a vast cosmos, random fluctuations might occasionally produce complex arrangements of particles purely by chance. In principle, one of those arrangements could briefly resemble a functioning brain complete with a moment of awareness. This idea is not meant as a literal description of reality, but rather as a philosophical puzzle reminding us how strange probability can become on cosmic scales. Most scientists view such scenarios as theoretical curiosities rather than likely events. Yet the thought experiment emphasizes an important point. Consciousness sits at the boundary between physics and philosophy. It is where the objective description of the universe meets the subjective experience of being alive within it. Despite all our progress in understanding matter, fields, and spacetime, the nature of awareness still invites wonder, and perhaps that is fitting, because consciousness is the lens through which every discovery is made. The universe has produced minds capable of asking questions about the universe itself. Now, as our journey comes to a gentle close, it is worth returning to where we began. The apple still rests on the table. Its surface reflects the light of the room. Its atoms vibrate quietly within the deeper patterns of quantum fields. Those fields exist within space-time, which may itself arise from deeper structures of information or mathematics, and within this vast structure, a conscious mind can reach out and hold the apple in its hand. It can feel the smoothness of its skin, taste its sweetness. and wonder about the nature of reality. Perhaps the deepest lesson of this exploration is that reality may be richer and stranger than our senses first suggest. Beneath familiar appearances lie layers of structure stretching from the smallest quantum fluctuations to the largest cosmic horizons. Yet the everyday world remains meaningful. The apple on the table is still an apple. The breath rising and falling in your chest is still your breath. The quiet room around you is still the place where your experience unfolds. And somewhere between the mysteries of the cosmos and the simplicity of this moment, reality continues to reveal itself, softly, patiently, and endlessly. So as the questions settle and the mind grows calm, you can simply rest within that quiet awareness. The universe is vast, its mysteries are deep, but for now the apple is here, the room is still, and your thoughts can drift gently toward rest.